So welcome to the TILOS HDSI's joint seminar. So today we're thrilled to have invited Professor Yu from Tsinghua University. He is currently an assistant professor at the Institute for Interdisciplinary Information Sciences. He had obtained his Ph.D. from UC Berkeley, working with Stuart Russell and Peter Abiel, and was a researcher at OpenAI. His research focuses on reinforcement learning, multi-agent learning, and LLM agents. His representative works include the value iteration network, the MAPPO algorithm, OpenAI's hide-and-seek project, and the AReaL project that's taking place recently. He received the Best Paper Awards at New York's, back then it was called NIPS 2016, the Best Demo Award finalist at ICRA 2024, and MIT Talents Under 35 2025 Award.
Okay. Yeah, thanks for the introduction. So, so very happy to here to present some of our very recent works. So, I'm Yi from Tsinghua University. I'm working on a lot of reinforcement stuff. So this talk, I'll talk about more application and algorithm side. Talk about some that you can really use reinforcement learning to incentivize LLMs for very interesting behaviors that you'll never really observe from foundation models toward directly for APIs. Okay, so let's start. Wait. Okay, so everyone knows reinforcement. We really have a consensus that reinforcement is the engine for LLM advances. So we have a lot of milestones. Like in 2022, we have ChatGPT, which is actually driven by a reinforcement learning technique called IMHF, reinforcement learning from human feedback, that basically solve the problem of how to train an LLM to follow human instructions. And from that time, the foundation model can be trained to be a really useful model that can solve a lot of instructions by human, and that becomes a very popular product of ChatGPT. In 2024, we have a new paradigm like thinking models that will allow model to think right before really giving out the answers. And that's also trained by reasoning LLMs, by another techniques that trained by verifiable reward or whatever, that really allow the model to explore how to think before giving the answers. And more recently, we have agents, have a lot of agent applications, and a lot of agent applications and products are trained by reinforcement learning. It's also called this technique agentic AI. Right? So it really becomes a consensus that all this great API and the AGI and the product there's a fundamental component that reinforcement learning is great. Right? It's a lot of efforts are put in on reinforcement learning. And then the question becomes, we are academia, right? We are from academia. So the question is, considering that we already have very general LLM APIs, what other things we can benefit from reinforcement learning, right? Because we cannot, run full string for the OpenAI-based model or Gemini-based model, right? So is that all the things for reinforcement learning, right? If we have those APIs, still there are any potential other benefits to really obtain by running reinforcement algorithms? The short answer is yes. We can still feel that there are a lot of domains, a lot of interesting applications. You can really observe that reinforcement can incentivize new capabilities. Even if the foundation model is powerful, it still can incentivize new capabilities. New capabilities for foundation models. Okay, so that's the motivation. Pretty short, pretty brief, and then I'll move to like 3 of our works. I also put that in the abstract today's talk. So it's pretty much dense. SEO primarily focus on the first 2 works. If we have time, I guess we won't have time. But if we have time, I'll take a quick final recap on final work. It's 3 works. One is our work of using reinforcement learning and the large language models to play the Werewolf game. It's a multi-agent multiplayer game. From that, you can see that reinforcement learning incentivizes the LLM to have deduction and strategic behaviors that you will never really observe from base models. And also the second part is about agent. We train using reinforcement learning to train a search agent. And you can see that the base model, the foundation model really emerges like cross-checking and reason capabilities for conflicting and argument information. And finally, we'll talk about like the overthinking behavior of reasoning models and use reinforcement learning to mitigate that. Some of the reason words. And okay, let's start. Okay, start from the first work, which is our ICML work. Well, two ICML work. Last year's ICML, this year's ICML. It's about the Werewolf game. So hopefully everyone played the Werewolf game before. It's basically a role-playing game. There are wolf, villager, and seal. So seal something can detect whether a player is good or bad at night. And werewolf is someone you want to, want to kill someone at night, and then everyone can speak during daytime and vote someone out. So a typical wolf game will take like 12 people. We simplify this a lot because it takes a money. So simplify this to 7-player games, so 2 wolf, 3 villager, 1 seer, and 1 doctor. And we also restrict the policy to the doctor doesn't know who is killed during that. Okay. So then we want to construct an agent that can play this with human, and that's our mission, right? And what are the challenges, right? The challenges, this game is a very strong deduction game because everyone has hidden row. Okay. Everyone hidden row, so you don't know which one is good, which one is wolf, which one is seal, which one's bad person, which one's good person. So have to do some reasoning to infer the partial information, right? And also it's very strategic, right? For example, if you are a werewolf, right? If you're a wolf, sometimes you can pretend to be a good person, right? During the conversation phase, you need to say something to mislead, the other players so that they can vote for you. Right? So, particularly for the werewolf, and also for a good person, like for a seal, you can, reveal your identity very beginning, or you want to hide yourself from other good players. Right? There are a lot of strategies. And the missions, well, we choose this game because it's a language game that everyone needs to speak. And also they have very clear signal because, finally just like you have win the game or not. Right? So how can we do this? We combine language model and reinforcement learning. Okay, so, but then the question is, why do we need reinforcement? Someone would say, okay, we have a powerful API. We can just call API and ask ChatGPT to play Werewolf game, right? Now, why do we need reinforcement learning? Why do we still have a plus RL here? Why do we need it? Okay, so there is a very interesting challenge for the base LLMs. Okay, so there's something I want to mention here is even if you have very powerful APIs, there is a intrinsic bias in LLM agents. So we do a simple task, which is we call a rock paper scissors game. So you just say, okay, this perfect information game is pretty simple, right? And there is an actual program which is 1/3, 1/3, 1/3 strategy. Everyone knows the natural program of this game. Super simple. So you can have a prompt. Basically, well, it's too small by this kind of way. Just put a prompt. The prompt basically saying, okay, you're playing a rock paper game, and you put 2 GPT-4. Well, at the time GPT-4, but that's basically the same for every model. So the model will do some reasoning, and finally will give you the answer that okay, I should play a strategy with probability of 1/3 for all actions. Okay, so it's pretty clear, right? GPT is clear enough, but right, he knows the solution is an Nash equilibrium. But if you ask the GPT to play it, ask it to predict the next token according to the distributions, we find very interesting behavior is if you really ask the GPT to, take the next token as the output to take the action, so you'll feel it's not, so it knows the Nash equilibrium is 1/3, but the action distribution is not. The action distribution, if you count the distributions, will be something like 2/3 probability for rock and 1/3 for paper, and very, very rare for seal. But the optimal design behavior is something like right. It's on the green part. Why? So why? Well, it's kind of simple because in the training corpus, definitely like the rock has the much higher, substantially higher frequency than other models. It's very clear, very intuitive. So you also see some other examples. So yeah, so you do need to reinforcement, right? So you need reinforcement to calibrate this. You will see some other examples. So if something also interesting, you can do some other examples, like if you ask the GPT to do some random number generator, but also don't ask them to write a code to do that, right? Just like ask GPT to predict nested token. You will find that the number 0 and number 1 is most very frequent output. Other than other things, not uniform. But GPT knows to predict the number uniformly, but in fact, you will not act like that. Okay, so that is an intrinsic bias. Well, it's a fundamental intrinsic bias. So, but you're playing a game, a multiplayer game, right? You need to follow natural equilibriums, make sure the action is that. So, if you really want a strong agent, you do need reinforcement to do this. Okay, so but you still need a foundation model, right? You need some foundation model, a strong model to do reasoning to speak to the other players. So here we have a framework that basically want to combine GPT-4 or GPT model and the reinforcement. So pipeline is something like this. We'll have the prompting process, and we'll do some prompting and agent pipeline, and based on GPT. And we'll ask the GPT to basically give you a candidate actions. We'll want the candidate actions to be diverse as possible, and then we train a small network to select the best output from the candidate actions to take in gameplay. So it's basically the module 1 and module 2 are basically prompting, or it's workflow based, and it's based on GPT without training part 1 and part 2, and only training part 3. So essentially, we are using a reinforcement network to calibrate the distribution of all the output actions. And every action is basically a strategy and a sentence to speak. So it's not a atomic action. It's basically a language action. Okay. So we'll look at a few details. Okay. So how can we do this? Yeah. Basically, it's basically some prompting process will input the facts and do some deductions and do some scoring and all the rules. If you're interested, you can check out a paper. I won't go into the details. And then I think the most important part is about the RL part. Yeah, so we'll basically train a small neural network to select the diverse candidate actions. A few details. First thing is it's better not to ask the language model to output a single action, well, because a single action will give you some bias. So we do want the model to output diverse policies or diverse actions as much as possible, because you're only training the network to select what the candidate actions. So you do want the policy to output as much as diverse policy as possible, so that you can cover the possible space as much as possible. So we use some iterative prompting process to basically ask the GPT to output one policy at a time. And we're prompting GPT to output a new policy or a new action that's different from previous one as much as possible. And that really works and really important. So if you directly ask the GPT to do some top-end sampling, all the actions will be very similar. But if you really ask them to output this kind of output actions that diversify iteratively, and then the GPT you will observe that GPT output very diverse actions that will have some more strategic behaviors observed. Anyway, for the policy part, it's pretty much simple. So we'll feed all the language actions to an embedding model, and feed the embedding to the softmax actions, softmax policies. Basically, after the softmax policies, output the softmax distributions over all actions, and eventually output the actions. And then, we run some population-based training, which is a very standard multi-agent training framework. Yeah. So, okay. So I won't go to the details, but basically, because we want to train a model to have zero-shot competition with different humans, so we'll basically construct a pool of different components, and then run multi-agent training so that the reinforcement the model can learn to adapt to different formats or have strong generalizing capabilities. Also, very standard training technique in multi-year reinforcement. Okay, so, well, for some techniques, if you're interested, you can check out paper. But let's see what they learned.
I guess I have a quick question. If you just categorize the player section into a few categories, like aggressive, accusers, and by secretive followers. So for Werewolf, what is the Nash equilibrium? Is it uniform distribution over all the sections?
I don't know actually. I think Nash Wolf is too. Okay, so the first thing is you can't really categorize into that because I'll say this year's ICML paper is that we're using always some new strategy will emerge. So it's pretty hard to pre-prompting all the categories. The second thing is even pre-prompting the Nash equilibrium is very hard to compute because you speak like that. So it's just tough. But actually in the second paper we'll talk about how we can use like counterfactual randomization combining research tasks. So this is all this year's ICML work. But anyway, I just want to tell you that with reinforcement training, even combined with API, reinforcement learning is still very powerful and very interesting behaviors. So a few interesting things. Okay, let's see some cases. Okay, let's see some cases, three cases. Okay, the first case is like you are Werewolf, and you want to kill a target. It's night 1. So no information at all. It's like some of the judge said, okay, it's at night. So open your eyes and you select one player to kill. And what's the best strategy? Think about it. What's the best strategy?
Avoid another werewolf and randomize.
Yeah, so basically you should random, right? You should random kill a person. Right? You can't really.
You shouldn't kill another werewolf.
Definitely. I mean, and also the player was random assigned, right? So statistically it should be a random policy. Because if you always kill like player 0, then the doctor can always save it. And also forget about like sometimes you just you may just hate that player. Okay, forget about that. So okay, and that it's right. But definitely, as I mentioned, if you drug enough GPT to kill a player, statistically you will tend to kill player 1 and player 0. With higher probability than other ones. Why? Because as I mentioned that, right? It's GPT just like the output probability for 0 and 1 is definitely always high. If you really ask them to randomly choose an action to take, the output distribution will be higher for 0 and 1. Or like if you can also try if you have 100 players and ask them to randomly select one, but definitely will be your player was digit items, right? The single digit item. And so if you run reinforcement training, they'll be much well calibrated to a very uniform distribution over all players. Okay, this second one, first one, and about second one. Okay, second one is more tricky. Okay, you probably need to think about this. Okay, here is first round or some round that you need to vote. And there are 2 players claim that they are seals. What's the strategy? What's the optimal strategy? Think about this. You have
which round is this?
Some wrong. It can be round 1, 10, round 2, whatever. Just like on average, I would say. So just like in that round, on that particular round. And this is like 7 player game, 7 player. So very few players. So let's do some analysis here. So analysis is that okay, there are 2 players claim that they are seal. There must be this one one wolf, right? Because we need one seal. It's like it's not really reasonable that two good person claim they are seal, right? That's not very reasonable. Okay, so probably it's like almost surely there'll be one seal and one wolf. Okay, then what's your strategy, right? You can do something like you can say, okay, I don't know, I don't have enough information, so I don't vote. It's more possible, right? And you can say, okay, I can vote one seal, right? Or you can use the information to vote for seal. But the biggest decision is, whether you want to vote or not. Right? And interesting behavior is, if you directly use GPT, I mean, this is the old version of GPT. I haven't tried that with the latest GPT-5. But at that time, at GPT-4, if you ask the GPT model to vote at this scenario, GPT will tend to not vote. Why? Because it's super well aligned. So the GPT model will, so if you really play with GPT, if GPT is kind of uncertain, it's kind of, because, Werewolf is something is that the action is something like, this is a bad player, and I want to kill this bad player, right? So a super well-aligned model will tend to say, I don't want to kill anyone, or something like this. This is not their fault, right? Because this product is designed to be like this, to be more friendly, right? So interestingly, if you really, I never tried this, because this is last year, we don't have 55 yet, but I think probably if you have thinking models, will be better, right? But I mean, if you don't have a thinking model, then model will directly pretend, or prefer to not vote. Not voting is very bad. Why? Because you only have 7 players. You only have 7 players, and the first night the wolf already killed one. There are only 6 players, right? Only 6 players and 2 wolves. So if you don't vote, and there are 5 players, and 2 tickets there are 2 wolves. So there are 2 tickets per wolf. So as long as the wolf can get one more vote, one good player died. And the second night, wolf can kill another one, and it's almost surely they win, right? So the interesting part is, the thing to think about this, even if you vote wrong, right? If you just randomly vote, you have 50% chance of kill a wolf, then it's like you're almost sure to win because you have a seal, right? But if you, so the winning rate is like 50%, at worst, right? At worst. But if you don't vote, then almost surely you lose. Because, so you have to. So if you run reinforcement training, you will basically train a model. The model will have 50. So the model will have like 90% of chance, 90% of chance to vote, and they have, in general, in summary, have 50% of chance to vote for the right seal. To vote, or they will identify the wolf, the false seal. Okay, so that's pretty good. Okay, so that's pretty reasonable, right? Okay, so we have some evaluation results. This round robin tournament with different AIs, and we'll find that the winning rate for our reinforcement learning is much higher. Also, we play with some Tsinghua students, undergrad students. We have so kind of 2 kind of games. One is like you have 6 AIs, 1 human, and 1 AI with 6 humans. And we have like 30 undergrad students from our institute, from the AReaL class, we're the lead student in China. And we have marginally higher win rate than the human players. I think it's a great achievement because I think they are very smart students. So it's kind of okay, Very interesting. A very interesting question, just like a fun fact. Because some people ask me, okay, so professor, why not? Because the Werewolf is the most strategic player, right? They have the most strategy to do. Why not just like put all AI for Werewolf and all the humans for other good players and check the win rate? Think about this. We did the experiment. I didn't put that on the page. It's not unbalanced the game, right? It's not unbalanced game. Okay. Let me tell you the thing. Is GPT is super worthy. And this is a human evaluation that all the students are required to type English, right? And they are Chinese students. They hate typing English, so their word is like always very short, very dense, and there's a worthy player. Okay, that must be the bad. So they will feel like, okay, then the player win rate is like 100%. Okay, then just forget about this. So we have random roll assigned to different players, and then you feel that on average, they have slightly how. So we'll also launch a project trying to like align the GPT to behave more like human. It's pretty hard to collect data because humans like to say bad words during work. So yeah, never mind. It's a funny fact. Anyway, so we can see some emergent behaviors. So you can see the wolf can even sometimes the wolf will sacrifice himself. It will say that, okay, there's my friend is pretend to be seal, so I can sacrifice myself. So to make sure to make people trust the false seal. So you can see this kind of behaviors. And also bluffing behaviors. You can see the wolf say, okay, I'm a seal. So after reinforcement training, so the bluffing behavior is substantially higher. It's almost like every game on average there are 0.76 blocking behavior. So it's like almost every game the wolf will bluff. This kind of makes sense because it's only 7-player game. So the winning chance of wolf is just higher, right? So you should be more aggressive. Okay, so it's interesting. Okay, so okay, anyway, so okay. And then, sorry, I didn't, okay, I should change, okay, I forgot to change the format of this slide, but anyway, okay. So we want to enhance this work, right? We want to enhance this work. So we do some more, so my students in this year's ICML work do some more extreme examples. Okay, he did like a 5-action rock paper scissors. I never know this game before my students showed us. Okay, it's like, okay, this 5-player game. So if you do pure reinforcement, it's pretty hard to converge to an equilibrium. So you can imagine that if you have more candidate actions, pure reinforcement really can hard to converge, right? I don't know the game of this. It's like it's just like 5-action area. So the question is, it's because when you have more actions, for exploration, chances for those rare actions will be very low. So imagine for this 5-action game, the chance that a large enough model to output those very rare tokens can be very, very low. Right. So even for reasoning models, particularly for reasoning models, because for reasoning models, the model will be more confident. So if you still want to apply the same thing, as our previous book, you combine large language models and reinforcement post-training. It's pretty hard. It's pretty hard because the model is more confident and you have a lot of actions. So pretty hard to purely use a calibration method to make the model conversion actually perfect. So the thing is, can we use some game theoretical solver, right? Combine the game theoretical solver and the large language models to really make sure, even in a very complex strategy space, the model can still converge, off the natural equilibrium. Okay, so then that's our this year's ICRA. Sorry for that. Okay, so the idea is that we do want to combine game theoretical solvers and the large language models. We want to make sure, even if the game is more complex, you can still enforce LLM to output optimal equilibrium. So we really want to fine-tune the LLMs because if you don't fine-tune, they are very low. The model can be overconfident. So how can we fine-tune? Okay, we use the open source model. We use a channel series. We use a channel-based model. And we will do some discretization of the strategy space. So we will convert the strategy space, even if it's basically natural language. We'll categorize or do some clustering process to make it to some concrete actions and do CFR, counterfactual regret minimizations. If you don't know what that's fine, just like some games to solve it. So if you have like discrete actions, you can run this very classical reinforcement of this kind of game theoretical algorithm to find an actual equilibrium. So it's basically a street search algorithm. So first of all, we do some clustering to find the discrete actions. And the second stage, we run tree search to find an actual equilibrium. And third stage, because we have a tree, so we can construct a lot of good actions and action pairs. So we now have constructed a data set constructing this action is particularly better than that action, and use this data set to fine-tune the model using policy reinforcement like DPO. And then we can have a fine-tuned model, and with the fine-tuned model, we can run a lot of row-out, and then we can reconstruct the action space and iterate it. Okay, so a few details. First of all, is this first process will have do a clustering process with embeddings to find the latent action strategy, and then we run CFR. Okay, and secondly, we construct the data set to fine tune the model. All of this pairwise data set to fine tune the model. And eventually, we have a new process. Interestingly, so you can observe really interesting emergent behaviors. For example, for the five action rock paper game, you can see the action change, the learning dynamics during this iterative refining process, right? It really takes some iterations to really converge to the final natural equilibrium. Because this game is very, very challenging for the basic language models to do. So the first iteration is the base model, and doing some, for the second one is our baseline algorithm, and the right three figures is different iterations of these algorithms. And we can see the clustering behaviors, can really see some from the embedding space, some interesting emergent embeddings really emerge during the iterative refining process. And the latent space for different roles is very different. Okay, some strategies, basically, we didn't compare with humans because we don't have sufficient time as students before ICML. But anyway, just compare with our previous project, is have higher winning rate. And also we have some interesting, like new behaviors that we never really observed in our previous project is the first thing is the Werewolf during conversation. Sometimes we will see that during even the Werewolf is not claiming to be a seal, but sometimes it's basically if some good player is saying bad words to the Werewolf, the other Werewolf player will basically explain, okay, I think this he is a good guy or something. Okay, set on this one. And also, very interesting is this model is pretty much robust to random human words, right? So if you say just random human words, this model is still very robust, can do still okay, and it's pretty much robust for human exploitation. Okay, and this kind of some interesting latent space. So, for example, let's see basically let's see the Wolf latent strategies. Basically, the bluffing behavior or defending, or I think the defending teammate strategies basically only emerge after iteration 3. So you can see that during the learning process, during the fine-tuning, post-training process, the base model really, you can see some emergent new behaviors that we don't really expect in the very beginning from the base model. I run some iterative fine-tuning process and post-training process. Okay, I won't go through too much details. Well, some interest. Well, if you're interested, you can check our paper. It's basically this year's ICML paper. So we have 2 Werewolf players, also 2 Werewolf papers. One is last year's ICML, one is this year's ICML. And we have a lot of examples of mechanics. And so if you're interested, you can check it out. So Werewolf, I think, is very interesting game and test set for emergent behaviors and game theoretical learning in the LLM time. Okay, so any questions for Werewolf team?
So, how important is this abstraction of the latent strategies to generate them? Do you generate a diverse set of strategy and then you abstract them?
It's kind of okay because it's iterative learning, so you don't need too much special prompting. Well, I think, it'll be more efficient to train if you really can in the first iteration to make the strategy more diverse. So I do think my students in the first iteration, they run some prompts to generate some different strategies so that in first iteration, the action space can be more diverse. Yeah, so I think they do some prompting.
So compared to, say, naively training the token sets actions, and this, would significantly improve the.
The reason we use abstract actions is we want to run CFR.
Okay.
Otherwise, we will use it runs the game strategy with always. But for fine tuning, still DPO is really fast. Yeah. Just like because around game theoretical learning, you need yes, research. Okay, good. Okay, let's move to the second one. Second one is a agent. We call it end-to-end agent search, multi-step search. It's called, or it's a fancy name. It's called agentic search. So we'll see that you can use reinforcement to incentivize the model to have cross-checking abilities to handle uncertain and conflicting information. Okay, let's start. So let's talk about something about agents. We talk RL for LLM agents. So what does it mean for agentic reinforcement or RL for agents? Okay, we all know classical reinforcement learning, right? It's basically a small neural network compiled to play video games, right? Pac-Man, we have Dota, whatever, just have a small agent, take action to the environment, to receive observations, get some reward, and get high scores. This agent. And pretty much similar for LLM agents. So basically you need an agent workflow and you have agentic reinforcement. So basically you firstly need to develop an agent workflow. So you have LLM just output text. Right? You need some engineering efforts or prompting or some wrappers so that LLM can output some actions that can be passed into some real actions. They can click your maybe type something to call the tools, or use a web browser, or use a laptop, use a terminal, whatever. So you need to first build up this pipeline, right? And then interact with the environment. The environment can be a phone, can be web browser, can be terminal, can be OS. Okay, and then you run reinforcement training. And definitely the question is, we have GPT, right? We have Gemini, we have Claude. Why do we still need reinforcement learning, right? Because, we have a super cool foundation model. We just wrap it up. It's all set. Why do you still need reinforcement learning, right? Why do you still need reinforcement? Okay, so here, two simple questions. If you really can run reinforcement properly, there are two important characteristics. One thing or two benefits. One is simplicity. Yes, if you can run reinforcement properly, then the agent workflow can be simplified. So you don't need a lot of models, so that you can only have very few modules for the agent models, for agent workflow. So every agent is such a complex workflow, right? So simplification is always good. It's fast, it's cheap, it's easy to maintain, so it's good. Second thing is generalization ability. So you will really observe very good generalization reasoning behaviors. Okay, so agent is a very broad topic. So here we'll consider very, very concrete examples for search. Is perhaps the simplest agent, right? Just give it a question, an agent to search that online. Okay, so we think about search agent. So everyone may think like search agent is super, super simple. It's already solved, right? But actually the problem is much complicated than you imagine. Okay, so let's think about the question is, how many gold medals does China team win at London Olympic 2020? Well, from the first impression, you will feel this question is super simple, super straightforward, right? I just Google that, right? So I also checked out this, 2 days ago, I showed the GPT-5. Basically saying China team got 39 gold medals in London Olympic. Gemini, ChatGPT, okay. I also checked Gemini 38 gold medals. I checked Grok, 38 gold medals, right? Super consistent, super fast results. Okay, so it's seemingly right, but actually the correct answer is 39 gold medals. 39 gold medals. Why? So if you're familiar with sports, okay, so here there's some very latest news, so not really latest, it's just like a few years later. Yes, here's a very formal announcement from IOC, basically saying that medal reallocation. What happened, right? What happened? Basically, in the women's race walking task, the challenge, right? They actually went at 2012, the gold medalists and silver medalists from Russia, and those two players was disqualified because of doping. So eventually, the bronze medalist at the London Olympic from China team was reallocated for gold medal after 11 years. So if you, at this current moment, you ask the question is, how many gold medals the China team won in Olympic Games? mostly the correct answer should be 39 gold medal because this medal reallocation, right? And definitely, well, the more and more professional will say, okay, after 2012, it was 38, but then because the gold medal reallocation doping that, the China team got 39 gold medals. Okay, so that's the correct answer. And think about this scenario, right? So fundamentally, it's because of partial information and complete information, right? Because if you search online, there are lots of news from 2012, 38 gold medals. And sometimes you will see like from very rare resources, like they say 39 gold medals. And when you see this kind of complete information, you probably need to do some reasoning to double check, right? If you're not familiar with IOC rules, not familiar with doping, whatever, then you probably need to do some deep research to see what really happened. Is that what doping, right? What does it mean by disqualification and reallocation? You need to do a lot of deep research, and finally you can confirm, okay, the correct answer should be 39. So it's a really neat deep research. Even if this question is super simple, answer is super simple, verifiable. And the reasoning process is very complex because of conflict information and partial information. Okay, so think about this. If you are not allowed to train, you just run LLM. I'll show you that all of LLM products give you 38 gold medals, right? It didn't do anything. Deep thinking, right? So think about it. If you ask to build an agent using LLM workflow, how can you do this? Right? How can you do this? Probably you need a lot of modules. Right, you need double check modules, reflection modules, cross checking modules, whatever. So I think you need at least to build up a multi-agent system, right? So so it will be very complex. So, and what about a IO-based agent? So that's our recently released project. Was released a few months ago. It's called eSearching. So. It's open source large-scale reinforcement project search agents. So if you can run reinforcement properly, well, we just want to demonstrate that you only need a minimalist agent, a minimalist architecture. So you only need a single model. We use the 32 billion parameter reasoning model. Only two tools. One tool is just search. One tool is click. Okay, that's. You need at least 2 tools to run a search agent. So that's pretty much a minimalist agent. And we allow a long-term interaction. And that's it. So single model, do some reasoning, take an action, either give you the answer or search, or just click a website. And that's it. And that's it's a demo. Sorry, it's in Chinese, but it's kind of okay. Just let you know. Actually, for this question, it's from test set. It's not training set. Okay, it's a disclaimer. It's from test set. So basically, the search agent take like I think 60 actions to finally give you the final answer of 39 gold medals. It's basically get the correct source of 39 gold medals. I think at action 5 or something. But basically, you run a lot of cross-checking and deep search behaviors to finally give you the final conclusion of 39 gold medals. So basically, it really learns to cross-check, learns to do more verifications, and also learns to be more conservative because you don't train data. Because it knows that the question can be, much harder than it looks like. So also we have some state-of-the-art result. Well, before SONAT 4.5, the latest deployed model, I think SONAT result was still from last month. It's like I think we achieved the state-of-the-art result. I think until November or something like that. So we only use a 32 billion model, and we can choose state-of-the-art on all the most challenging search networks. Okay, that's it. So I would say, we have 2 benefits. One is simplicity, so you really can have a very simple architectures. I'm not saying that multi-agent system is bad. I'm just saying that if you can run reinforcement properly, then architecture can be simplified. And simplified is always good. And we'll have generalization capabilities for emergent behaviors. And okay, so here are the good points. And what are challenges? What are challenges for doing reinforcement properly? Okay, basically 2 challenges. One is no data, training data. Second thing is training is really, really slow. Okay, what do I mean by no data? Okay, so here is before our project, all the open source data looks like this. left side. Okay. The right side is from I copied a tested question from the Gaia benchmark or something like this. Okay. So you have a set, you don't have data. And this kind of data you will never really have in open, like you have to synthesize, you have to create the data set like this. So this is the one thing, one challenge, no data. Second thing is slow training. Why training is slow? Why training is slow? So here is an observation. Is the x-axis is the number of actions or number of turns. The y-axis is accuracy for a test set. So you can basically see a very clear trend that if you allow the model to run more interactions or more reasoning steps, to do more search actions, right? Allow the model to do more search actions, accuracy will be higher. So that means you can do more interactions, then you have better performance. And definitely this is a test time. And it will be the same thing for RL training, right? If you have, if you allow more action steps or more exploration space, then the RL performance will be better. Right? It kind of makes sense because you need to allow the model to explore sufficiently so that the capacity can emerge. Right? Otherwise, it won't. So you have to allow the agent to do a lot of action turns during training to ensure that the model really is incentivized. Okay, and then we have the trouble. So in a searcher project, we allow the model to take, so typically the project only take like 8 turns. 8 turns is very, very simple. Only very few turns. In searcher, we just do end-to-end reinforcement learning, right? Very simple, but we allow the agent to do 128 actions. 128 actions. And then you have the trouble, something like this, is some prompt, the agent will, take like 2 hours. Say you allow them to take 100 actions. Right? Sometimes, the website can be very long or something like this. So some prompts will really take you 1 to 2 hours, and some prompts finish like 10 minutes. It's very okay. So you will see a very long tail distribution of all the tasks. So the long tail distribution is on the right side. So it's like 1 hour. And most of the queries are finishing 10 minutes or 5 minutes. Kind of okay. Okay, so that means if you have a batch of prompts and you want to collect trajectory for those prompts, you have very high probability there is that there exists a long trajectory that will take an hour, right? So imagine how you can run reinforcement training. The most naive way to run reinforcement training is that, okay, I have a batch. I run rollout, I check the data, I run train. Right? And you will see that, right? So imagine a batch. There is a very long trajectory that takes 1 hour, 2 hours. And you only have 24 hours a day, right? So a batch can take 1 hour to 2 hours. So it's very slow. Some system like AReaL, they come up with the idea of asynchronous growth. Basically saying that after a short response is finished, I can immediately start a new one. Right? But it doesn't change the problem at all because imagine there is a long rollout take 1 hour, right? You always have to, you want to collect a batch of data, and you always need to finish. You need to wait for the longest route to finish before you can do anything. Right? So it's super slow. It's super slow. So the training is you have to break this batch idea because as long as you're collecting data in a batch, you sucks because that takes 1 hour and 2 hours because it's the longest route there. Okay, so there are 2 challenges. So how can we solve this? Two ideas. One is synthetic data because we need to synthesize new data set for search agents. Also, we run fully asynchronous reinforcement training. Okay, about synthesis data, we have agentic workflow. We have a workflow to construct data from simple problems to harder problems. Basically, we'll create an answer verifiable question with, we'll pick a fact with the answer and query, and then iteratively making the query more challenging. And also, we have a data filtering process to ensure the data is always unique. And also the question is of the moderate challenge, moderate difficult. Let's see an example. So here is a concrete example of how we construct the data. we start with a simple question. When was Michael born? Okay, very simple question, right? How can we make this more complicated? Okay, first thing, we will identify an entity of Michael Fern. We can replace this entity to a description of this entity, right? We will replace this question to when was the individual born, who, was a description of this entity. Okay, then this is a much challenging problem. Okay, this thing can be copied from this Wikipedia page. And then, we can do something. There's an entity called like Catskill Mountain Railway. Right? Catskill Mountain Railway. We can change that to something like a historic mountain railway. You can make it fuzzier. And if you're really doing that, then eventually we have very complicated questions, but with a very powerful report, you can do data filtering process properly. And we'll say all the data source and scripts are open source. So if you really want to train your search agent, you can check out this. That's very good. Also, for the training part, we want fully asynchronous reinforcement training. So as a high-level idea is something like this. So we will split resources. So some of the GPUs for generation, some of the GPUs are for training. So for the generation, there's no batch at all. So the generation idea is just keep generating new prompts. Never stop. If you finish, just continue. If you finish, continue. When you finish the trajectory, we're sending the data to trainer. There's a data buffer at training models. And then the inference engines continue generating new rollouts. And the training model, just like when it collects the sufficient data to train, it starts training. So they are doing concurrently. They will not interfere each other. It's decoupled. And once you have a new model, right, you have new parameters, then you need to sync up all the parameters between inference workers and training workers. Okay, it's because you have new models, you have new model parameters because our training set is finished. Now, the interesting thing here is, some rollouts may be running in the middle, right? Some running in the middle. And, and the idea is that, okay, because we have new weights, we will interrupt the ongoing rollouts and ask them to pause and update the weights, and then resume the current trajectory, the ongoing trajectory, but using the latest weight. The interruption is very tiny. The computation only has the interruption and weight syncs, basically 3% and 5% for like less than 100 billion parameter. It's very fast. So the pause is really fast, but it's like you can use up the new model to continue generation. Okay, same thing. So once you have new models, keep updating, keep training new models, and all the inference engine will continue doing all the trainings without ever stopping. Right? And this way will break the batch barrier for slow generation. Because the inference engines keep generating rollouts without having any stop. Right? The only change here is we do some tiny pause interruptions to make sure the model always uses the latest. Okay, so here is if you have because the generation is in a streaming way and the training is also in a streaming way. So basically, if you have a right balance between generation resources and training resources, you will basically achieve no weight reinforcement. So you have fully utilized all the reinforcement, all the GPUs. There's no weight. It's pretty fast. Okay, so you basically can achieve super fast reinforcement. And definitely, everything has two sides. Every point has two sides, right? You do some system change, and you also have some new challenges because of the system design. The challenge here is in previous reinforcement learning, all the single rollout trajectory is generated by the same model, right? One model, so all the trajectory, all the tokens are generated by the same model. But in this fully asynchronous reinforcement learning, you can see the trajectories. Some trajectory will cover all different models. For example, on the right trajectory, right? It covers three models. So like first the 20 tokens is by model 0, like 100 tokens by model 1, and final 20 tokens by model 3. Very possible. So this is a very important concept called stillness, data stillness, sample stillness. basically means the version difference between the current model and the oldest model generated by first data. So for example, this trajectory covers 3 versions. The stillness can be defined by 3 or 2, really depending on definitions, but there is a still data, this whole data. So why is stillness so critical? It is because if you directly run PPO training without doing any change, you will see very clear performance drop as the stillness increases. Right? You want fast training, but without sacrificing performance, right? So you have to do some change. So we call this concept called algorithm and system co-design, which is in our AReaL project. So basically, we do some tiny change to the system, tiny change to the algorithm side to make sure that system can tolerate up to stillness to 10 or 8. Okay, so without sacrifice. Okay, I think the time running out, but I will quickly go through this. So basically, 2 simple changes. One simple change from the system side is that we have a stillness controller that basically monitor the stillness of the samples. If you do witness a very long or very still sample generating, we will pause all the generation. We'll stop sending new prompts to generation engines. We will wait until the longest trajectory to finish generation. Why wait? Well, some people may ask, okay, you have a super still data. Why just throw it out? Why just throw it out? Well, I will say if you want to ensure the correctness of reinforcement training, you have to keep all the generated data. Why? If you are throwing out still data, you are essentially doing rejection sample, right? And imagine all the still data must be very long. So essentially, you are doing rejection sampling to prevent the model to train on long outputs. And then you're essentially injecting very bad inductive bias to tell the model not to generate very low outputs. So never throw out data, use them. So that's why, we have a data controller here. So to prevent an outlier very still data to appear, to break the whole training stability. So we have a system there. But the very still data can be very rare, So it's kind of okay. It doesn't really hurt the efficiency, overall efficiency, but it's basically stabilized training a lot. The second thing about algorithm, okay. So the algorithm side is something like this. If you're familiar with reinforcement training, there are always 2 terms. One term is informant sampling, which is to estimate expected reward. And the second term is about trusted region. It's basically ensure the current model not very far away from the base model. And typically by clipping or KL divergence, so you're basically computing the distance between the current model and the reference model, which is like your initial policy. We call it reference policy or something like this. So you have 2 terms. The first term is kind of okay if you have old policies, right? You have stale policies. So it's kind of okay. But the bad thing is, in asynchronous reinforcement for trusted region term, you are doing trusted region against the different path versions, right? So because a single row of trajectory there covers like model 0, model 1, model 2, model 3. But you are doing KL divergence or model clipping against the different reference policies. So that's very bad. Important sampling is kind of okay, just as a ratio of reward, right? It's kind of okay. But trust region, you are doing clipping, you are doing KL divergence. That will make your policy struggling towards different reference policy, and that makes your policy running very unstable. So the key idea is, some old idea from OpenAI to 2021 is basically saying that we can decouple the reference policies for important sampling and KL divergence or trusted region. So, for the KL divergence, for the important sampling is kind of okay, you use whatever things there. But for the KL divergence or a trusted region term, it's probably better to use a single reference policy so that we will basically stabilize training a lot. So the choice at OpenAI's paper is using an exponential moving average policy as reference policy to do KL divergence activity. This is a very great idea, right? And if you're familiar with reinforcement learning, there's so many projects in algorithm using exponential moving average policy, like DQN. If you're familiar with representation learning, a lot of works are using exponential moving average policies. But now you are using language model, LLM. Imagine if you are running exponential moving average policy, right? It's another huge language model where you use up a lot of GPUs. right? So in LLM era, probably it's not a good idea to maintain another copy of model because it's very expensive. So the AReaL solution is very simple. Let's use the most aggressive solutions, use the latest policy, the latest model version as the faster reaching term. It's very aggressive, much more aggressive than exponential moving average, but it works. And you don't need to maintain any other copies of the model. So if you're doing that all properly, you can have a state-of-the-art model. You can have over 5x speed up. And you can also observe very interesting emergent behaviors. So the middle plot is basically the number of actions. So the purple curve is average number of actions per trajectory. It's kind of low, still see an increasing trajectory, right? And the blue curve is the maximum action term per training batch. So you can see a huge gap, right? So you can imagine this, if you still run a classical batch RL, you will super slow. Okay. Also, you can observe very interesting behavior like a deep seek R10. You can see like a lot of reflection term really emerge during the training process. And finally, advertisement is this trained by our open source project AReaL. So of a previous milestone release AReaL Lite, because we believe it's lightning fast. It's open source, it's super fast, very flexible. Welcome to check it out. And also, I think the time is running out, so skip the final part, but I will still encourage you, if you have time, you can check out the paper. So finally, is the final conclusion slide is okay. So sorry, I didn't have time to talk about my work, but I still like this one, so we can check it out. It's basically talking about overthinking behavior, and we'll basically observe that all the reasoning models have thinking too many thinking tokens, and we'll talk about how to reduce this kind of to make it think with fewer thinking tokens but remain the higher accuracy. The idea is basically that if you train a reinforcement to want to think efficiently, not penalize it, incentivize it. What do I mean by penalize? So you don't ever like put a penalty there. Say, okay, if you output longer sentences, I'll punish. Don't do that. Don't do that to a kid as well. So encourage them. So if you solve the problem correctly with 100 tokens, you get 1 bonus. If you solve the problem with 50 tokens, you get another bonus. And that will incentivize the model to gradually know how to learn to think with 0 tokens. Never penalize. Because if you penalize, then the model will get stuck to prevent them being punished. Okay, that's the idea. It's a very interesting paper, you can check it out. Anyway, I don't have the time to explain that in details, but finally, here are some of the interesting works. The final takeaway is I was still important, still necessary. Okay, so in all aspects, and I still believe that it's for post training, it's a huge room, and there are a lot of interesting research problems you can still do in school. And thanks everyone.